Let us see 3D curves and surfaces in computer graphics. This presentation includes curves, quadratic surfaces such as spheres and ellipsoid, superquartics such as super ellipse and super ellipsoids. Curves. 3D curves can be drawn from an input set of mathematical functions, or we can draw from a set of user-specified data points. When mathematical functions are specified, a package can project the defining equations for a curve to the display plane and plot the pixel positions along the path of the projected function. Here is an example. The data points are nearby the curve, and here it is approximating the curve, and this data point is on the curve, that is interpolating the data point. And quadratic surfaces means it's a frequently used class of objects which are described with the second degree equations. That is quadratics. Second degree equations we can call it as quadratics. These include spheres, ellipsoids, parabolic and hyperbolic. Here are the pictures of quadratic surfaces: sphere, ellipsoid, elliptic cylinder, elliptic paraboloid, parabolic cylinder, quadratic cone, hyperbolic cylinder, hyperboloid of two sheets, hyperbolic paraboloid, hyperboloid of one sheet. And let us see sphere. In Cartesian coordinates, a spherical surface with radius r centered on the coordinate origin 0, 0, 0 is defined as the set of points x, y, z, and it should satisfy the equation x square plus y square plus z square equal to r square. Value of x coordinate, value of y coordinate, value of z coordinate, radius. And sphere in parametric form. Here it is represented in xyz plane. This is x-axis, y-axis, z-axis, xy plane, yz plane and zx plane. Then point P is of radius r from the origin, and P coordinate of P is x, y, z, and phi is represented as latitude angle and theta is longitude angle. And using this formula we can do this: x equal to r cos phi cos theta, and y is equal to r cos phi sin theta, z is equal to r sin phi, where phi belongs to phi is in between minus pi by 2 and plus pi by 2, and theta is in between minus pi and plus pi. Here is ellipsoid. It's an ellipsoidal surface which is the extension of spherical surface. Here the thing is that radii of this one, Rx, Ry, Rz, are of different values. This Rx is different from Ry, it is different from Rz. This Rx represents the radius in x coordinate. This Ry represents radius in y coordinate. Rz represents radius in z coordinate. These all values are, three values are different. And the Cartesian representation is represented by x by rx whole square plus y by ry whole square plus z by rz whole square is equal to 1. And in parametric representation, we can represent x as x equal to rx cos phi cos theta, y is equal to ry cos phi sin theta, and z is equal to rz sin phi. Here phi is in between minus pi by 2 and z plus pi by 2. Theta is in between minus pi and plus pi. And here is superquartics. They are formed by incorporating additional parameters into the quadratic equations, and generally it is used to increase flexibility by adjusting object shapes. Here number of additional parameters used is equal to dimension of the object. Here one parameter is used for curve and 2 for surfaces. Here are different superquartic forms. Two types are super ellipse and super ellipsoid. In the case of super ellipse, the Cartesian representation is like this. Here we are using exponent coordinate s. That is x by rx whole raised to 2 by s plus y by ry whole raised to 2 by s equal to 1. Suppose if the value s can be any real value. Suppose if the value of s is 1, then the equation becomes s by rs whole square plus y by ry whole square equal to 1, which one is the ordinary ellipse. And equation we can represent as x equal to rs cos raised to s theta, y is equal to ry sin raised to s theta, where theta is in between minus pi and plus pi. Here are the super ellipse. Here rx equal to ry and s is different. S is represented by this value. Here s is 0.5. We will get the figure as like this. And for value 1, the figure is like this. And 1.5, the figure we will get the figure as like this. And for 2.0, this one, 2.5, this one, and 3.0, like this shape we will get. And a Cartesian representation for a super ellipsoid is obtained from the equation for an ellipsoid by incorporating two exponent parameters s1 and s2. The equation is x by rx whole raised to 2 by s2 plus y by ry whole raised to 2 by s2 whole raised to s2 by s1 plus z by rz raised to 2 by s1 is equal to 1. And if s1 and s2 are 1, then we will get the ordinary ellipsoid. Then parametric representation we can write as this one. It's equal to rx cos raised to s1 phi cos raised to s2 theta. Y is equal to ry cos raised to s1 phi sin raised to s2 theta. Z is equal to rz sin raised to s1 phi, where phi is in between minus pi by 2 and plus pi by 2. Theta is also in between minus pi and plus pi. The figure illustrates the super sphere shapes that can be generated using various values of parameters s1 and s2. We can put s1 and s2, various values for s1 and s2. These super ellipsoids and other superquartic shapes can be combined to create more complex structures such as furnitures, threaded balls, and other hardware. This figure is super ellipsoids plotted with different values for parameters s1 and s2 with the radius is same, rx equal to ry is equal to rz. This one is s1 represented in x-axis, s2 represented in y-axis. These are the figures, super ellipsoids. Reference use this one is here. Thank you for watching.